In examples 5 and 6, we want to find a function that corresponds to the graph of the given polynomial. We can start off in example 5 by pretty easily identifying our x-intercepts, which occur at 0, 0, 1, 0, and 2, 0. Using that information to start filling in our function, we know that we're going to be dealing with a function that looks like f of x equals x minus 0, which would give us that first x-intercept, x minus 1, which would give us our second intercept, and x minus 2, which would give us that third intercept. Investigating the behavior around those intercepts, we can see that at 0, our function will touch the x-axis and then turn away. So we know that that multiplicity has to be even. Since we want the multiplicity to be even, and we're told that we want to use the smallest degree possible, our smallest even number would be a 2. At x equals 1, again, our function touches the x-axis and then turns away. So we would want the smallest even multiplicity we could apply. And then at x equals 2, our function actually crosses over the x-axis. So our smallest odd multiplicity would be a multiplicity of 1. We've got almost everything in place there. The one last thing that we need to account for is whether or not there's a constant factor being multiplied out front, like we've seen in some of our previous examples. To find what that value for a should be, we'll consider our y-intercept, which is the point 0, 0, and we'll substitute those values in for x and y into our equation. So substituting in y equals 0 will give us 0 is equal to our value a times, in place of x, we'll substitute in a 0, minus 0 squared times 0 minus 1 squared times 0 minus 2, that quantity to the first power. This will give us 0 is equal to a times 0 times negative 1 times negative 2, or simply 0 equals 0, which means we can substitute in any value that we want for a, and this expression will still be true. Our simplest value to substitute in for a would be 1. So if we let a equal 1, then we'll just have x squared times x minus 1 squared times x minus 2 to the first power, or just x minus 2, as the function that corresponds with that given graph. In example 6, we want to do essentially the same thing. We can identify our x-intercepts, which occur at negative 2, 0, negative 1, 0, and positive 1, 0, meaning our function, let's call this g of x now, will be of the form x plus 2 to give us that intercept at negative 2, x plus 1, and x minus 1. Considering those multiplicities, we see that at x equals negative 2, our function crosses over the x-axis. So we'll want an odd multiplicity. We'll use 1 as our to continue pursuing that smallest possible degree. At negative 1, our function touches the x-axis and then curves away, so we'll give that an even multiplicity of 2. And at 1, our function crosses over the x-axis again, so we'll use an odd multiplicity of 1. Then we'll need to find what value we would want to substitute in for a for that constant factor. We can again look at using our y-intercept, which in this case would be the point 0, negative 1. So letting y equal negative 1 will give us negative 1 is equal to a times 0 plus 2 if we let x equal 0. 0 plus 1, that quantity squared, and 0 minus 1. Which will give us negative 1 is equal to a times 2 times 1 times negative 1, or negative 1 is equal to negative 2a. Dividing both sides by 2 will give us a is equal to positive 1/2, meaning our function g of x that corresponds with that graph to the right would be the function 1/2 times x plus 2 times x plus 1 squared times x minus 1.